So a while back I was taking this Intro to Stats class, and one of the most important topics that we went over was the standard normal distribution, which is modeled by the Gaussian integral. Now the Gaussian integral tends to be a pretty tough integral, but I think it has a really fascinating solution, and I want to go over that one right now. Just keep in mind that we are going to use multivariable calculus to solve this. So the first thing that I'm going to do is I'm going to let I equal the integral from negative infinity to positive infinity of e to the negative y squared dy. Now the reason that we're able to do this is because we've just set this up as a dummy variable, and we're assuming that these two integrals are the same. So basically what we have here is our original statement in terms of y, and when we square that we can actually keep it in terms of x and y, and what we have is the integral from negative infinity to positive infinity of e to the negative x squared dx times the integral from negative infinity to positive infinity of e to the negative y squared dy. Our next step is to combine these integrals, and when we do that, we are left with the double integral of e to the negative x squared times e to the negative y squared dx dy. And since we're combining two exponential functions with the same base, we simply have to add the exponents. And what we're left with is the double integral of e to the negative x squared plus y squared dx dy. Now, I've put a little note here that is just a reminder to account for the Jacobian correction. And you'll see that a little bit later when we change the coordinate system, but the first thing that we want to do is evaluate the first integral, and it's actually not that difficult because what we're going to be left with is just simply 2 pi. And when we account for that, our next step is going to be to use the polar coordinates to evaluate the integral. And we do this by letting r squared equal x squared plus y squared. What we can do beyond that is use a u substitution, as I've done here, where I let u equal r squared so that du is equal to 2r dr, and then I divide both sides by 2r, and I'm left with 1 over 2r du is equal to dr. So now I'm going to go ahead and I'm going to account for that first integral like I was talking about back in this step over here, and that, like I said, is just going to give us 2 pi, and we're left with the single integral from 0 to infinity, and after using the u substitutions, r times e to the negative r squared dr. And finally, the integral seems more intuitive now because we'll plug in our u values, we'll plug in our dr, and what we're left with is I squared is equal to 2 pi times the integral from 0 to infinity, and of course we have to make sure that we have to make sure that the limits match up, and they do. In fact, when you plug them back into our statement here, we do see that the limits do not change. You still have the integral from 0 to infinity, and we're going to do some simplifying here. So we'll cancel out these two r's, and these two can also cancel, and what we're left with is I squared is equal to pi times the integral from 0 to infinity of e up to the negative u du. This is a pretty simple integral, and what we find is that it's equal to negative e up to the negative u, and of course we're going to use the fundamental theorem of calculus to go ahead and find the value of this function. And what we have is I squared is equal to pi, which we got from here, times negative e up to the negative infinity, and it's going to be minus negative e to the negative 0 power. Now, this minus sign, when we combine it with this one over here, is going to make this entire sign positive, which I've noted here. And negative e to the negative infinity is just 0. So what we're left with is I squared is equal to pi times 1. Or in other words, I is equal to negative pi.